Okay, so dear participants, it is my great honor to introduce Harvey Friedman, a man whose work has reshaped our understanding of mathematics and its very foundations. Harvey's story is already legendary. He has no high school or master certificates. Instead, at the age of 17, he had completed his PhD at MIT. At the age of 17, he became the youngest professor in the world, joining the faculty at Stanford. From these beginnings, he went on to spend most of his career at Ohio State University, where he became distinguished university professor. He started his career at this university in 1977. This remarkable trajectory was not just about being a wunderkind, it was the first sign of a lifetime of intellectual audacity, rigor, and vision. Harvey Friedman is famous for being the founder of reverse mathematics, a program that asks a deceptively simple question. Which axioms are exactly needed to prove the theorems of ordinary mathematics? With this idea, Harvey gave us a new lens through which to view the whole mathematical enterprise. Suddenly, classical theorems could be calibrated with great precision and their hidden dependence on logical principles revealed. Reverse mathematics grew into a fast international field, and it continues to guide research today. But Harvey did not stop here. He went further, developing what he called strict reverse mathematics and later Boolean relation theory and tangible incompleteness. These programs uncovered entirely new landscapes where finite combinatorics and infinite set theory intertwine, and where even familiar theorems demand the strength of large cardinals. Again and again, Harvey showed us that the frontier between the finite and the infinite runs straight through the mathematics we thought we already knew. His contributions have been recognized with some of the highest honors our profession can bestow. In 1984, Harvey received the Ellen T. Waterman Award from the National Science Foundation, the United States' highest prize for young scientists. He has delivered distinguished lectures across the world, the Gödel Lecture, the Rademacher Lectures, and the Alfred Tarski Lectures, to name just a few. He is a Guggenheim Fellow, and in 2013, Ghent University awarded him an honorary doctorate. Yet, perhaps more impressive than the honors is the sheer consistency of his intellectual output. For decades, Harvey maintained nearly continuous NSF support, and his influence is visible across logic, philosophy, and even computer science. He has trained generations of doctoral students who now carry forward his vision, building a research lineage that spans many areas of mathematics. And there is another side to Harvey that not everyone may know, his deep love of music. He is an accomplished pianist and an expert on producing fine-tuned pieces on an electronic piano. It is also worth noting how others have written about him. In 1985, we see the book Harvey Friedman's Research on the Foundations of Mathematics. Over the years, Harvey's ideas have been features in the notices of the AMS, in Science, and even in popular science outlets like New Scientist and Nautilus. Writers have drawn not only to the technical brilliance of his work, but also to the philosophical depth. The way his results force us to confront the very limits of knowledge and the necessity of new axioms beyond those we once thought sufficient. In short, Harvey Friedman has given us far more than individual theorems or programs. He has given us a culture of precision about the strengths of mathematics, the courage to push beyond all boundaries, and the inspiration to see logic not as an abstract museum piece, but as a living, evolving discipline that touches every corner of our subject. Personally, I had the luck of being involved in less than 1% of his work, but I am happy being able to find the phase transition for Kruskal's theorem and certain natural versions of the Bolzano-Weierstrass theorem. Finally, let me point to the Ghent lectures of Harvey on tangible incompleteness, which can be found on YouTube. As you can see, Harvey, now 76, still produces world-class mathematics. Thank you.
Thank you very much, Andreas. Uh, and with this beginning, let me give the word to Professor Friedman, please.
Okay, I was wondering who you were talking about for a while there, but thank you very much, Andreas. Uh, I'm very excited to to receive this invitation from Lev to give a kind of talk I always dreamed of giving, but would be just too autobiographical and too ambitiously speculative for normal venues. So this is going to be unusual fun, and I'm thinking that I might build further on these remarks and ideas in future communications. So, uh, let me, um, yeah, I'm just having a little trouble doing this second here.
Mhm.
Yeah, let's go over I just want to read the abstract again. Uh, the abstract, in case you haven't seen it or don't remember it. So I'm a foundationalist. I will talk about my foundational adventures from ages 7 to 77 in mathematics, piano, and chess, and as expected, ambitions go far beyond limited achievements. The foundations of mathematics, by far the most highly developed and successful corner of foundations, with foundations of computer science a distant second, has a great future not only in and of itself, but also as a guiding force to ignite the other comparatively backwards foundational enterprises. Um, so I divided this talk into four parts. Foundational adventures while in school, um, and this is somewhat autobiographical. Some successful adventures in the foundations of mathematics, which is uh, the core of the talk as far as logic is concerned. The future of the foundations of mathematics, highly speculative and ambitious. Um, and finally, remarks on general foundational adventures um, outside foundations of mathematics. Um, okay, so foundational adventures while in school. Uh, so I think I always was had a distinctly foundational bent. I remember two occasions well before seven, if I can recall, that must have seemed odd to my parents. My father was in the photo typesetting business and something of an inventor, and my mother managed the business. Both had only high school educations, and our home was in Highland Park, a northern suburb of Chicago. On one occasion, I saw this book on the table. It was called a dictionary. And I saw that you're supposed to look up words there and get something called definitions, which were meant to say what that word means. And I remember looking up some basic words like large and more and good. Their definitions would, of course, use other words. So I looked up some of those other words and then did some more of this. To my frustration, I quickly found cycles where the original words I was looking at appeared later. I decided that this dictionary was full of these cycles, and so nothing really got defined. I could barely wait till my mother got home to tell her how worthless this so-called dictionary is. I remember she patiently listened to me and just told me that lots of people buy dictionaries anyways, and we were still going to keep it around the house. On the other occasion, I remember some groceries were delivered to the house and I got interested in the bill. I was pretty good at addition, and I wondered what happens if you add the bill up after changing the order of the prices. So after some experimenting with this, I found that the sum did not change even if I changed the order of the prices. And I don't think that I was surprised by this one way or the other, but I got very curious about why is this so and how could this be known generally? So this was, I don't remember the exact ages, but well before 7. All right, I was around 7 when my father started me on piano and taught me how to play chess, and more about that much later in the talk. Um, a couple of years later, an older kid down the block gave me his used first year algebra book. I got fascinated with his book and worked it through on my own. I got familiar with his exercises of the form, with the exercises of the form, solve the equation 3x plus 2 equals 11. And um, and after learning to do such problems, I began to think about what it means to solve in this context. I always had the idea of mathematical statement as opposed to solve, solve being an imperative and hence radically different than a mathematical statement. So I came up with the idea that to solve in this context is to establish existence and uniqueness. And I remember formulating the statement for every x, 3x plus 2 equals 11, if and only if x equals 3. Uh, so I was actually more interested in the logical structure of this algebra than this algebra itself. That's the point I'm trying to make. And I was more interested in the adding the bill and the generalized commutative associative law than I was in the groceries. Uh, okay, so let's fast forward to high school. I was accelerated 1 year when the school system saw I got 100% on a calculus final in a hot, humid 1960 summer school at the University of Oklahoma. Um, Maybe a factor in my favor was my parents had no significant college, and I'd done that. I became aware of Bertrand Russell through his important book, Introduction to Mathematical Philosophy, 1919, where he does a very good job for the time of laying down the set theoretic foundations for mathematics. The book ends with, if any student is led to a serious study of mathematical logic by this little book, it will have served the chief purpose for which it has been written. Well, I certainly can attest personally that this book has definitely served its chief purpose. Um, so I devoured this Russell book, and I remember telling my father that I felt great with this kind of thinking and I was going to pursue it as far as I could. I remember meeting William W. Tate, the University of Chicago Philosophy Department, and discussing the first order predicate calculus and axiomatic systems with him. I remember being in his car and getting so excited about this stuff that he made me stop talking to avoid getting into a car accident. I also met Ruth Barkin Marcus, Roosevelt University at the time, later Yale. And in interacting with both of them, I became aware of the distinction between foundations of mathematics, philosophy of mathematics, and wider philosophy. I later became aware of the many philosophical books that Russell wrote and remember reading An Inquiry into Meaning and Truth of 1940 book. And I tried to make precise sense of this book as I did with the mathematical philosophy book, but was never similarly satisfied. I grapple with the relationship between foundations and philosophy to this very day. I applied for early admission into MIT and saw something very exciting in the course catalog. It was an advanced graduate course in set theory to be offered by Hilary Putnam on consistency and independence of the axiom of choice and the continuum hypothesis. Kurt Gödel had already shown the consistency in 1940 publication, and Paul J. Cohen had just recently shown the independence. I realized that this was the solution to some main problems essentially raised in the Russell Mathematical Philosophy book and more, something I had my heart set on working at when I got to MIT. Naturally, I was excited about learning this stuff, even if it was already known. I got early admission into MIT, arriving there for 1964 to 65.
How
Uh,
old were you back then when you got admitted? Something.
MIT.
Yeah,
15 and 11 months.
15 years old. Yeah.
I quickly met Hillary Putnam, who was at MIT philosophy at the time, and thereafter at Harvard philosophy. Hillary was at MIT briefly, yeah, before he went to Harvard for the rest of his career. I viewed Hillary as my accessible foundational hero, Russell being inaccessible, in England at the age of 90. At that time, I think it was 94 or something, uh, and and Gödel becoming accessible only much later. I I'll talk about my meeting with Gödel. Um, during his first semester, during my first semester, I took one semester of mathematical logic from Hartley Rogers, um, MIT math department, and got a decent grounding in mathematical logic with Mendelssohn's book, Introduction to Math Logic, I think it's called. This gave me enough background for Hillary's spring semester course that included the new Cohen breakthroughs. It's actually rather impressive that somebody most well known for his work in philosophy, although he did some considerable logic, uh, uh, seized on the Cohen thing and actually taught it. Hillary was assisted by then MIT graduate student Richard Boyd, Cornell philosophy. I mentioned him. He's a pretty famous philosopher. He spent his career at Cornell. He was at MIT at the time. And I learned this important material. Cohen called it forcing, as many of you know, with their help. Oh, a digression, which is more connected with the later parts of the talk. Soon after arriving at MIT, I found a fairly comprehensive collection of textbooks being used for MIT courses in virtually all subjects. There was a floor. I tried to investigate what exactly that building was and all that. That seems to be a little complicated because it was changed to a student center and this and that. But anyways, there was this floor where they had almost all the textbooks used for almost all the courses, uh, undergraduate courses, maybe some graduate courses, but mostly undergraduate, in virtually all subjects at MIT in a convenient distance from my dorm. We used to hang out there. I think it was open 24/7, in fact. And I remember deciding that the state of knowledge was in a disorganized, mutually incomprehensible mess. That the cure, being a unified foundation for everything, is the cure. I remembered carefully planning my future intellectual life based on remedying this situation. This is the starting point for the last part of my talk. Uh, okay, during my second year at MIT, I took Hillary's course at Harvard on hierarchy theory, hyperarithmetic, ramified analytic, constructible hierarchies. I began to formulate some original PhD level research programs and was taken on by advisor Gerald Sachs in the MIT math department. Now, Gerald was a prominent mathematical logician, recursion theory mainly, and he didn't have the same kind of foundational orientation like Hillary or Russell or Gödel. See, he wrote a paper called Remarks Against Foundational Activity, which gives you an idea of where he's coming from. Uh, I don't know whether you've seen that paper, but you can search on it. Remarks Against Foundational Activity. Okay, I remember one foundational adventure at the time that I didn't fully pursue, but others have. I remember Gerald telling me about Abraham Robinson's interest in formulating axiomatic systems that take infinitesimals as primitive, with the expectation that you get provable sentences not mentioning infinitesimals that are not provable without the use of infinitesimals. Uh, uh, that was his goal. I readily came up with such appropriate systems, taking non-standard elements as primitive and so forth. One gets the opposite of this expectation. You get a conservative extension. And Robinson, being the founder of infinitesimal analysis, was, according to Gerald, rather disappointed with this. Actually, I think he was Gerald said that Robinson was kind of annoyed by this. So another foundational adventure was a principal part of my thesis. I had the idea of formulating the axioms of set theory without parameters. What I mean here is that the parameters are all given by explicit definitions. So the parameters are explicitly defined as the hypothesis of the parameters. I prove that this subsystem of ZF has the same logical strength as the full ZF system. And I offer this up as a philosophically significant reduction of ZFC. In other words, ZFC can be interpreted, ZFC is consistent relative to this reduction when they make the parameters explicitly defined. And Hillary criticized this as an illegitimate reduction from the philosophical point of view, and for very credible reasons. Nevertheless, I felt there was something here of real significance in this reduction, and that it had some sort of fundamental significance, even if I couldn't express what it was. So it was only much later in 1981 publication that reductions to parameterless subsystems became the essential tool in an entirely new kind of tangible incompleteness called Borel diagonalization, something of clear foundational interest.
So by parameters, you mean here the free variable that occur in schemata like
Exactly. The free
separation and so
variable
on
is
and so
no
on.
longer a free variable, but it's if x equals the set of all x such that psi, where that has no parameters, then you can use it.
Yeah.
And for pairing, you would need two such parameters, right? And so forth.
Mhm.
In general, on any number. All right. So after Gödel, and I don't think this idea of parameter of set theory without parameters or with definable parameters has been pursued too much, actually. Uh, but I heavily used it later in something
Mhm.
uh, 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 called Borel diagonalization. All right. After Gödel and Cohen established that the axiom of choice and the continuum hypothesis were neither provable nor refutable from the usual 1920 axioms for mathematics, mathematicians generally were anxious to know whether mathematical problems of a more tangible nature would also be neither provable nor refutable. I remember discussing this with many people and deciding to work seriously on this issue in the future. I neglected to say here, by the way, that I also discussed this with Cohen. Way after I was when I was at Stanford, not still a student here, um, and he said, I I played with the ordinals and the sets, but I didn't do anything with the integers. They're the same here, and I have no idea how to do anything like that. I mean, it was uh, fully recognized by Cohen the limitation of forcing for foundations. I mean, he uh, even though it was a great advance, he wasn't trying to hide that there was much more. There hopefully could be much more to the story. All right, so I received my PhD on September 21st, 1967, according to the MIT Museum. There's a thing called the MIT Museum, by the way, which is cute. They call it that. It gives official dates and pictures and whatever of events at MIT, I think. I haven't explored it much, but I did come across this. So now I
So
had two
that's a kind
degrees
of
in my name.
database of all the events, defenses,
Yeah, it
etc.,
seems to
with
be.
specific
Uh,
data. Mhm.
Definitely whether somebody got a degree or not is in there,
Mhm.
on a page. I had two degrees to my name now, one from the eighth grade and one from MIT. The eighth grade one I did really get. See, I had skipped the seventh grade because I got the 100% on a calculus exam, so
Mhm.
they decided that I could skip seventh grade. But there was an eighth grade diploma. I want to confess that I don't think I can find it. And I
But
promise
you
you,
know, you're not the only logician or let's say famous mathematician who didn't finish high school, so to say. That's
oh, I grew, well, there are probably many, hundreds.
there are several others. For example, Israel Gelfand, maybe you know.
Oh, well,
So he
yes.
was one of them.
Okay,
But
so I've
also
been
logician. There was a Russian logician, Alexander Kuznetsov, who did some
oh, I know the name. Yeah.
important work in non-classical logic, and he
Yeah.
never finished school. Yes, that's.
Well, okay. So,
Mhm,
anyways, some
mhm.
successful adventures in the foundations of mathematics. So let's talk about this. Um, Now, I'm not going to give an entire list of all the things I ever did. I think that would be kind of uh, too intense, right? But just some things. So I accepted an assistant professorship at the Stanford Philosophy Department starting September 1, 1967. My office was in the mathematics department, so I had considerable contact with faculty in both departments. In those early years, I got deeply involved in two. Oh, by the way, I should say, how did I get hired? I got hired, I had correspondence about subsystems of analysis with subsystems of second arithmetic with Pfefferman and Kreisel. And Suppies was the chair, Patrick Suppies was the chairman of the philosophy department. And I think you know this giant name, Pat Suppies. And and uh, and this offer was fixed. It was in philosophy. It was more complicated to do it in math. I think they put me in the math department for uh, for my office, and then and officially paid in philosophy. All right. So I accepted an assistant professorship in the Stanford Philosophy Department starting September 1. My office was in the mathematics department, so I had considerable contact, as I said. Those earlier years, I got deeply involved in two main foundational adventures. Uh, and to this day, one evolved into what is now known as strict reverse mathematics. You will see this with the parenthesis around strict because the public, the published opening of this was intended for reverse math, with strict reverse mathematics being something not really fine-tuned anywhere near enough uh, to uh, put forward at that time. But yeah, I'll talk a little bit about that later here. Uh, but so it's reverse mathematics that was set up. Uh, but the strict reverse mathematics is what I really had in mind. Reverse mathematics is strict reverse mathematics light. Okay. And the other survived into what is now known as tangible incompleteness. So I want to focus on the evolution of these two main foundational adventures, which are reaching new levels of success even during the last few weeks. Um, First, the strict reverse mathematics adventure. This started while I was still at MIT with hints of it in my thesis. You can sort of, but I really got into this when I took in the thesis, there's this idea of something being strong over a base theory and in a reversal in something or something like this. This started while still at MIT with hints of it in my thesis, but I really got into this when I took advantage of having my office in the math department at Stanford. I tried to impress mathematicians at the T's with the fundamental character of formal systems that arise organically from strictly mathematical considerations. Uh, these were typical mathematicians. What do you do? Well, you mention a formal system or something, and they immediately think you're some sort of strange logician who they don't want to talk too much to and can't understand, right? So I try to impress mathematicians at the T's with the fundamental character of formal systems that arise organically from strictly mathematical considerations. This was the idea. In this way, my original conception of reverse mathematics, which starts with a formal system called RCA naught, which does not rise organically from strictly mathematical considerations because of its axiomatic schemes, its schemes. In this way, my original conception of reverse mathematics was, in fact, what I now call strict reverse mathematics. And the relevant references are these, the first two being very well known. The ICM paper, uh, uh, which sets up reverse math, but I think with the full induction schemes. And then the right way to do it with the noughts, with a sub-zero, right? Uh, uh, those abstracts in the JSL. And then, so that set up reverse math, and everybody took reverse math. Well, interested parties took reverse math in that way, and didn't even think or care about me talking about strict reverse math. So the subject evolved, and then I got interested again in this. This is the foundation of strict reverse, finite reverse mathematics, strict finite reverse mathematics, this paper. It's called The Inevitability of Logical Strength. By the way, it has an interesting philosophical point. A real skeptic, which is actually the hidden opinion of many important mathematicians and unimportant mathematicians both, the hidden uh, idea is that all of these problems like Gödel has about consistency and all these difficulties, logical difficulties, stem from logicians writing down axioms that are much too strong. This is the implied quiet opinion, but which are much too strong, and you actually can probably do mathematics normally without any issues, any foundational issues or consistency issues. Of course, we do know that that's kind of true for real closed fields, right? Because you can prove the consistency of real closed fields, by the way, in exponential function arithmetic, although that's not so easy to do. If you go a little higher, it's easier, much easier. So I was very interested in the idea of refuting the idea that logic is totally worthless. I wanted to prove that it was actually worth something, so to speak. So I wanted to show that logical strength is inevitable. The only way you can show logical strength is inevitable is really to do some strict reverse math. So I came up with these axioms, which are purely mathematical, though, now, which actually literally logically imply exponential function arithmetic, so you can get going. So that logical strength, once you have exponential function arithmetic, I say that you have logical strength. And then you can go beyond that. Now, I gave some talks. Okay, so let me fast forward here. So this is a big expository paper in 2021. Talking about the detailed evolution in 110 pages of actually reverse math, and also the strict reverse math development. Now the strict reverse mathematics, actually, this is the strict reverse finite strict reverse mathematics. But the actual strict reverse mathematics is actually started here because there's a system in there called elementary function arithmetic, EFA, right? Whoops.
So by strict reverse mathematics, do you mean the reverse mathematics over some system conservative over elementary arithmetic or exponential function arithmetic or something else? So could you perhaps
okay, which are we talking about? Are we talking
about
the original? Are we talking about the original? In the original,
no. So now when you are so you call that original reverse mathematics is now called strict reverse mathematics.
The original, yeah, and the original reverse mathematics is called reverse mathematics. Okay, and that one.
And what is strict reverse mathematics, just in general terms? So what it is
Elementary theory of functions, ETF. I was confused. Okay, go ahead. Sorry. So what am I supposed to
So the
address?
question was just, you mentioned these two kinds of reverse mathematics, strict and non-strict, several times. So what is the main difference between them? So could you...
In reverse mathematics, you start with a convenient base theory and you don't care that it's full of logic. In other words, logical schemes, axiom schemes, RCA naught, for example.
Right.
In strict reverse mathematics, you do want to have a base theory because otherwise things are very disorganized. You do want some sort of base theory, but the base theory is made of strictly mathematical statements that you can look up either in the literature or are so commonplace and adjacent to the literature that it's strict mathematics, mathematics only.
Your base theory should be like that.
Your base theory is like that.
Mm-hmm.
In here, I gave
Mm-hmm.
two base theories. One is RCA naught, which is the real convenient one that everybody ran with, and another one called ETF. Not, there's a lot of EFEs going on here. ETF, Elementary Theory of Functions.
Mm-hmm.
EFA is another phrase between which is a standard system exponential function arithmetic. This
Right.
is ETF,
Mm-hmm.
elementary theory of functions. And I claim in this paper, excuse me, in these abstracts, that RCA naught is equivalent outright to ETF, elementary theory of functions. I claim they're equivalent without proof. And then since everybody ran with RCA naught and couldn't care less about strict reverse math, and the foundational issues surrounding all this. I never published that until I never wrote up the proof,
Mm-hmm.
publicized the proof until here
Mm-hmm.
later. It's in there in great detail, and then actually some people have actually written about that proof and and did something with it. So it's a real thing here. It's in here.
Okay.
Okay, but now that's the foundations of strict reverse math. But there's a thing called finite reverse mathematics, and actually, finite reverse mathematics actually also exists. People like Wilkie and other people have done this kind of thing where you go much lower than RCA naught, and you try to look at prime factorization, number theory things and so forth. There's a certain amount, and actually some of that stuff goes back to now I can't remember his name. Uh, in the Berkeley model theory volume, there was somebody who looked at very weak fragments of arithmetic. Uh, Pretty well known. I think I can't remember his name, but anyways, Shepherdson. Yeah, Shepherdson. Yeah. So this idea of going low and just looking at the finite mathematics. In other words, reverse mathematics of reverse finite mathematics is set up in here. Because in here I want to get to EFA and somewhat beyond. I want to get to EFA. I want to get to exponential function arithmetic and systems like that from nothing. That's the idea here. Okay. And when I say nothing, I mean from math, from simple strings, stuff like that. Now you understand that strict reverse mathematics is allergic to anything that looks like logic. You understand that? That's the point. All right. Now, okay. So if you want to know more about this, this thing here is worth looking at. And now, there's been a big reverse math meeting, as you know, in Vienna, just ended, 10 weeks. And so I was invited to give 3 talks there online on strict reverse math. Now that's a lie. I decided to get myself invited to give these 3 talks. All right. So to tell you the truth, okay. So and these three I gave in August uh, are by are a much more polished idea of what strict reverse mathematics is and how it can be developed is much more much clearer. This is the Bible right here.
Mhm.
Okay, so uh, and there are a lot more references. The whole history of are you going to use functions? Are you going to use sets? Where did I come? Where who mentioned this idea? Who did that? All this kind of stuff is in here. All right. So the original stuff led to quite a long-term, vibrant, steadily growing development of reverse math, as seen from the recent comprehensive 10-week meeting in Vienna. Remains to be seen whether strict reverse math will have the same kind of slow but steady compounding development that reverse math has. You know, you have to make it attractive for people to get into it and know how to proceed. Um, and So I think I did quite a good job with that. I think I could do a better job. I could probably do more. But one thing I think I mentioned it later in the talk. One thing I think that you can really dig your teeth into without getting into too much technicalities is there's a book, for example, Halsey Royden wrote a book on real analysis. This is somebody actually met it. Uh, at the T's, by the way, at the Stanford Math Department. He wrote this book on, which is at one time very widely used. I don't know if it's how much it's used anymore on real analysis. So the question is, what is the logical strength of this book? You need to talk about what is the logical strength of a book. You need to do strict reverse math. You don't want to pollute matters with logician's bias as to what uh, you have, right? So you want to organically take the book and reverse it, or if for a lower bound, and you want to for an upper bound you want to interpret the book in a system. With the upper bound, it's not an issue. You can use any logical tools you want with an upper bound. Uh, I mean, there's still you have to be careful how you do it honestly. I mean, there's a thing called honest calculation of logical strength. Okay. All right. So the other main foundational adventure covering basically 1967 to 2025 is what I call tangible incompleteness. Got this name, tangible incompleteness. In contrast to reverse mathematics, this has been predominantly a solo adventure, especially so since 2000. The idea behind tangible incompleteness is to greatly enlarge the scope of the spectacular incompleteness phenomena originating with Kurt Gödel in the 1930s and crucially supplemented by Cohen in the early 1960s and later others. For a variety of reasons, including the computer revolution, it is clear that the main thrust of mathematical thinking is drastically less set theoretic in nature than the comprehensive foundations for mathematics crystallized by 1920. Um, now, that is not meant to be a criticism of the of set theoretic foundations. That's not at all what I have in mind. I just want to contrast um, what mathematicians really care about compared to the full generality of the concepts in the foundations. That's all. I don't. This foundations is not being challenged in any way by what I'm saying. Okay, as one systematically descends down the ladder. So this I have sort of a new way to say this. As one systematically descends down the ladder from the lofty axiom of choice and continuum hypothesis statements treated by Gödel and Cohen through many critical levels down to, say, Diophantine equation theorems, there is a virtual exponential increase in the corresponding mathematical activity and interest level under virtually all measures. the highest level in this well-studied hierarchy for which the level of mathematical activity is too vast for anyone to have anything like full familiarity is arguably what is referred to as the Borel mathematical universe level. So let's see if I can make this clearer. If you say you're doing, you're interested in the mathematics that lives clearly in the Borel mathematical universe, and you say that I'm familiar with it all, I'm pretty much familiar with it all, you know that you're lying or you're crazy. There's too much. If you want to look at the mathematics that lives in the Borel universe, this is incredibly vast. But what if you say that I'm familiar with pretty much with all the things that have been done with the next higher level, and one next higher level in a detailed study of these levels would be the analytic sets, right? They're not Borel. And there's some pretty interesting stuff in there. But if you say I'm pretty much familiar with all the things that are done in the analytic sets and above, then that's plausible. And you can use maybe AI searches to actually, and various methods to actually quantify how much mathematics is of this character. And if you go into the projective hierarchy, and you say, well, I'm familiar pretty much with everything that's been done with the projective hierarchy, that's very plausible. You're probably uh, uh, you're one of the well-known set theorists, right? So but that's incomparably smaller than the mathematical world in the Borel universe. So you see that this is one way of talking about the stark importance and clarity of of these levels. Uh, you can actually put some quantitative measures on them, maybe you can put some quantitative measures on. And if you go below Borel, into continuous or you know things that are clearly within the first few levels of the Borel hierarchy or Bear hierarchy and lower. That would include all countable mathematics if you want. But if you were to do that, then of course you would be increasing the amount of mathematical activity and interest even much more. It would be even much higher. Got all this partial difference equations doesn't really go in. It may go into the Borel hierarchy, because of discontinuities, but it's not going to go, it's not going uh, into any kind of general Borel. Okay, so I like this new way of, I came up with this because I had to because Lev asked me to give this talk. So I became expansive about this, about this way of looking at things. So tangible incompleteness really has a point. You can kind of prove in some way that you're being sensitive to the actual state of mathematics, uh, in this way. All right. Now, I brought the incompleteness phenomena down to the Borel universe by the early 1980s. For a comprehensive account of the Borel universe level all the way down, from the Borel universe level down to very low levels, comprehensive as of 2011. Uh, you see, look at the introduction to the Boolean relation theory book, which is only online at the moment, but it's being formatted for publication now. There's an introduction that's 237 pages long, which is a pretty long introduction, and it's traces the history of of Borel down all the way. Now, how far down did this go, actually? This went down to pi 02. Uh, More about that later here. And the very recent stuff that's not at all covered in here is actually down to pi 01, you see. So there's something new going on. All right, so there is this introduction which you might want to look at. Um, Now, Borel diagonalization theorems are discussed, and this is where my foray into my thesis into parameterless theories plays a crucial role, despite its dubious direct philosophical significance of reduction. Uh, so there's a thing called the Borel diagonalization theorem, the first one, uh, which says that there's no way to make Cantor's theorem is given a sequence of reals, there's a real off the sequence, right? Take it that way. Now, there is a Borel function which maps infinite sequences of reals to a real off the sequence. And it's discontinuous and it's low level. And you can actually work on an interesting problem of exactly where that function can lie. So there's a Borel function which takes an infinite sequence of reals to a real off the sequence. But can you do it in a way that is invariant under changes in the invariant under permutations of the sequence that you're given, or invariant under maybe under finite permutations, right? Or invariant under the range. In other words, if two things have the same range, then you get the same answer. Can you make it invariant? And the answer is no. You can't make it invariant because that's a theorem that you can't make it invariant, but it cannot be proved in second order arithmetic. It has high strength. And how do I show it has high strength? Well, I use some work on parameterless. I look at parameterless second order arithmetic. Now, here the parameters are just not there. Uh, the parameters are just not there. It's not like the definable parameters. So it's a little even more basic. And it's not completely straightforward to show that that's strong. So, but that's what's used in the proof that the statement I mentioned is strong. All right. Now, my two adventures in tangible incompleteness since 2000 uh, are Boolean relation theory and invariant maximality. And the full BRT book is already here. Uh, uh, it was accepted for publication a long time ago, but I got the idea of I got to the idea of this new invariant maximality, and I just didn't follow through with this. So it's been sitting around, but it's going to be published. I was accepted by ASL series.
Mhm.
Uh, but it's there. I mean, pretty polished. I may have to do a little more polishing because I left it at 2011. Yeah. But anyways, invariant maximality developed later after Boolean relation theory. And invariant maximality has been going on for quite a while, actually, in some ways. But it's accelerated, and I now have a good portion of a book on it, the invariant maximality book on it. But already you can see two publications. One is in honor of Patrick Suppies, um, and this has reversals in it and proofs from large cardinals. And this one uh, is in honor of Hillary Putnam, and I changed the name to emulation theory. That's a bit of a long story, but it's basically the same. Maybe there's some small changes in what I was doing, and now the name is officially invariant maximality. Period. Changed it back.
Mhm.
Uh, there's been a lot of polishing and recasting of the things, and just basically the same kind of thing, but it's much more convincing. This is now in uh, this is what I'm talking about all the time. This is what Andreas has 20 or more recordings of lectures on this. Um, and serious improvements on earlier things and so forth. All right, we regard invariant maximality as a major improvement over the earlier Boolean relation theory on two counts. Firstly, BRT is at the level of explicitly pi 1, 2 and implicitly pi 0, 2. Whereas invariant maximality is at the level of explicitly pi sigma 1, 1 and implicitly pi 0, 1. Yeah, what do I mean here? Explicitly means what does it look like on the page without doing any coding or any dancing? What does it look like on the page? And Boolean relation theory is pi1, 2. It says all functions of a certain, discrete functions of a certain kind. I can find infinite sets of which uh, I could find a tower of infinite sets, which, or maybe even three. There's statements in there. Three infinite sets where there's a Boolean relation theory, Boolean relation between the sets and their forward images under the function. That's what Boolean relation theory is about. And those are pi1, 2. And it's proved that they're implicitly pi0, 2, because by all this logic and reversals, one actually proves it's equivalent to one con of large cardinals. So that's pi0, 2. Whereas invariant maximality is at the level of explicitly sigma 1, 1. Sigma 1, 1 with a universal number quantifier in front, by the way. But let's call that, I mean, they used to call that essentially sigma 1, 1. Let's just call it sigma 1, 1. Explicitly. Because it says if I have an order theoretic constraint, I can find a maximal set which is invariant. Hence invariant maximality. That's all it is. Well, I mean, that has to be explained a little bit, but basically that's what it is. And so that's sigma 1, 1. And it's implicitly pi0, 1. And that's done by proofs. One shows it's equivalent to con in a reversal that's already on my website. The Yeah, but also this book is planned to have chapters 4 and 5, which haven't been written. Chapter 4 will give explicitly pi0, 1, which is something I couldn't do over here very well. Explicitly pi0, 2. This didn't work too well in BRT. Explicitly pi0, 1 looks to be very promising. I mean, I already have things like this, but I think that it's going to get very slick. And I think that is a whole new thing, that it's explicitly pi0, 1, rather than implicitly. Uh, uh, Now, invariant maximality is definitely lower down the ladder because of this. Yeah. Also, I'm planning to do this with finite games as well. And that's going to be explicitly finite as well. All right. Anyways, both BRT and invariant maximality introduce new systematic investigations with surprisingly rich phenomena. Just looking at as math. However, invariant maximality combines two of the most commonly occurring themes in mathematics. Invariance in the sense of remaining unchanged or equivalent under certain changes, and maximal in the sense of not capable of being enlarged under a suitable constraint. So everybody is familiar with this all through mathematics. Invariant maximality shows that in very basic contexts, the combination of these two notions is profoundly explosive, taking us necessarily out of what can be handled with the usual 1920 foundations for math into large cardinals. And BRT is more specialized, although its connections with a range of mathematical environments is considerable. There are other kinds of connections BRT has with various mathematics that invariant maximality doesn't. So invariant maximality does not kill BRT. BRT still lives. All right. Now I should before I say this controversial thing, I should say that there's a literally finite uh, invariant maximality. I don't mean finite form. I mean the invariance. The invariance is respect to finite changes. Respect to finite changes. Uh, the full invariant maximality is you it is involves an infinite all right, I'm gonna say something. Let me not say any more about that because it could get confusing. But there's a part of invariant maximality that's done in straight mathematics that is done easily within RCA naught. There's a straight, purely mathematical form that's very attractive and looks like some regular combinatorial mathematics of a very attractive kind, just flat out. And there's no logical issues. And so I'm happy with that because mathematicians can take that and not be scared to death, and just develop it as as a standard subject. Uh, uh, okay, all right. Now, invariant maximality has been considerably proved, and okay, we think it's my opinion that invariant maximality is sufficiently compelling now after many recastings of it and simplifications of it that it's likely to be used in some perhaps more elaborate form, maybe, to prove results of pre-existing interest. In other words, this is actually going to connect with existing mathematics that has nothing to do with anything we normally do, and it's going to be used as a tool. I think this is going to happen because it's just too elegant and fundamental and basic. Too elegant, fundamental, and basic. It should be useful. Um, a book on invariant maximalities is in preparation. Invariant maximality, the book is called Invariant Maximality, Finite Free Choice and Finite Games. And here's some available documents, as this, is marched out. Um, there's the actual key reversal is done and on the website. It's numbered 126 on my downloadable manuscripts. The actual reversal in I don't know, 10 or 13 sections is actually in its gory detail in there. Uh, and
By the way, you will make your slides available for everybody to see these references, etc., because it's a useful guide
this document
to your
here.
work.
Of course, I
Mhm.
polished it up and wrote that this is the way I give talks. Of course, you're going to have this.
Okay. Some
Okay.
people asked in the chat about this, so it's
Yeah. Okay. So, and then I have lecture notes for the lectures on the little parts of this. And by the way, those lectures sometimes have errors in them, and they're corrected in the notes. So I mean, I do say some false things from time to time in there, uh, too often actually. But the written record is good. And so there's 20 lecture notes there on the downloadable lecture notes. And then there's over 20 recordings that Andreas has on his site. And so I'm hoping this book will really be done this year. I'd like to mention two other foundational adventures of interest. Each show that the two extensively used fundamental concepts are in fact unexpectedly equivalent. The first is relative consistency and interpretability of first-order systems. A very common way to prove that T is consistent relative to S, i.e., con S implies con T over a weak system, the so-called relative consistency, is to give an interpretation of T and S, right? It's the usual way, right? The result is that the two notions are equivalent. And I did this in a couple of unpublished places. And it has been reworked and appears in formal publication. I think that this is the probably the best place to look for this if you want. Visser uh, and I have talked a lot about interpretations, and he's an expert in this stuff. So he's got a proof of my theorem in here that relative consistency and interpretability are the same. The second concerns the intensively studied disjunction and numerical existence properties of intuitionistic systems. Now, any of you familiar with intuitionistic formal systems know this is front and center, the disjunction property and the numerical existence property. There's another existence property when you have sets. You ask for a definable solution to it, but I'm talking about the ones mainly are for arithmetic. These are for any systems, even if they're set theoretic. Uh, but I'm talking about the numerical existence property. And it's obvious that the disjunction property follows the numerical from the numerical existence property, right? There is an n less than or equal to one, right? And stuff like that, right? So the converse actually holds for any reasonable intuitionistic system. Uh, and this is a paper that appeared in the proceedings of the NAS. And to get in there, you basically have to have the paper communicated by a member. So I'm very proud that this thing appears with communicated by Kay Girdle. This is an ego booster of mine, right? Okay, so Girdle got interested in this result after I gathered the nerve to phone him at the IAS announcing it. And he invited me for a 2-week visit, and we went over the manuscript while I was there. I do remember pretty clearly when I met him in his office and he asked me a question, and I asked him a question I planned well in advance about the paradoxes, sir. I don't know if I used the word sir. I don't think he would have liked that too much. About the paradoxes, sir. What is the solution to the paradoxes? And he looked at me rather bemused. He shrugged his shoulders and he said, I can't say. And I said to him, the philosophers have been trying to deal with this forever. And he promptly said, what philosophy? And I have my own interpretation as to what that meant. Uh, I remember going back to my IAS apartment at the Institute, sat down and cried. I went to the I went to the mountain and I got essentially nothing, and I just went back and cried.
All right.
Okay. Now you have to understand,
Okay.
I was a lot younger, but I wasn't that young. I think it was in my late 20s at the time. All right. So what about the future of the foundations of math? Um, Now, how long do you want me to go on here? I was planning this to be ending at 10:15,
Right, but we took some of your time, right?
but you took some of my time. So how much did you take?
So let's negotiate. What time would be optimal for you for to finish your?
I think there's some exciting things here. I think that 10:30 would be good.
Yeah, let's do it at this
And I'll
time.
keep an eye. I got the clock, the digital
Yeah,
clock, right in my eye here. Yeah.
yeah, okay.
All right. Future of the foundations. I'll limit this just to my two most long-standing efforts. There's so many other exciting directions for the future related to my work and some others and some others. So and since I only have till 10:30, I'm not going to talk about the entire future of foundations.
Okay.
Okay, so number one, strict reverse mathematics will become. So I'm going to make these optimistic statements without proof. Okay, strict reverse mathematics become a thriving subject, much the same way reverse mathematics has become. I made a pretty decent start with this in the recent 3 lectures for the reverse math meeting in Vienna. Additional ideas probably will be needed to help jumpstart the SRM of carefully chosen mathematical topics. One project I put forth is to work out the strict reverse math of Halsey-Royden's real analysis text. I think that's something people could get into, uh, sort of knowing what they're up against, uh, without getting into the more delicate issues, the more difficult things in SRM, the more conceptually difficult things. All right, invariant maximality will have explicitly pi zero forms. Now that's already planned for the book under finite free choice. It's not quite crystallized. I'm almost ready to lecture on that with Andreas. Not quite ready, but it will have explicitly pi zero one forms matching or close to matching the existing invariant maximality and naturalness and simplicity. And that's going to be a big advance. because now there's no hint of infinity at all. In addition, all of the invariant maximality will be extended to correspond to the large cardinals. Also have initial work that I've done, but beyond the scope of the book. So there's a plan for book 2, which is large cardinals, which is invariant maximality and large cardinals. All right, invariant maximality will become a thriving area, much the same as reverse math. So now that I got reverse mathematics had this great history, I keep pointing back to it's my standard, right? This will occur even when invariant maximality still is focused on its currently purely order theoretic character. So, invariant maximality is purely order theoretic. Boolean relation theory isn't. There's some plus and times in there, and that's why it's pi02. Invariant maximality is literally order theoretic, and that means that you can see that the statements are pi01 just by their form. You don't have to go through the reversal to see that they're actually implicitly pi01, implicitly pi01. It's kind of surprising that you can just use order and get large cardinals and not have to think about even addition. All right, invariant maximality will be developed in a variety of contexts going well beyond the order theoretic. The concept of invariance and maximality naturally occur automatically in situations where nobody would even think of making it purely order theoretic. It's got the ring operate, the field operation, it's just all over. After all, invariance and maximality occur all over the mathematical landscape. At some point, invariant maximality will provide new insights to pre-existing areas of math. Now, I don't have a feel for whether invariant maximality, even properly extended, will touch Diophantine or transcendental number theory. However, I'm more optimistic about it providing missing combinatorial techniques or tools that will unlock the numerous major open questions in computational complexity. Where you take a Turing machine that solves SATs, right? And you somehow throw it into the transfinite, where it's operating in the transfinite. You do some combinatorics, large cardinal combinatorics, and then you pull it back down to get your and you get a contradiction. Something like that. That's exactly what I do in invariant maximality, by the way. Exactly. I take the original statement that's purely finite and I blow it up into a large cardinal, into the large cardinal, and I do combinatorics on that and I pull it back down. So that's how we're going to do all this P equals NP stuff and so forth. All right. Don't ask me how to do it. I don't. All right. There seems to be a way to arguably use invariant maximality in order to confirm the consistency of certain large cardinals. Invariant maximality statements can easily be naturally put in the form that certain non-deterministic algorithms of a simple kind have an infinite non-deterministic path. In other words, you're trying to build an invariant maximal set. That's what invariant maximality is about. Building it, you can definitely build it incrementally, in an infinitely long non-deterministic process. You don't know that you can do that except by the invariant maximality theorem, which uses large cardinals. But nevertheless, you have this thing. And now I'm going to abort that and just ask for the first 5 terms or the first 10 terms, right? Okay. So invariant maximality statements can easily be naturally put in the form that certain non-deterministic algorithms of a simple kind have an infinite non-deterministic path. Thus, a consequence of the consistency of large cardinals is that such non-deterministic algorithms have a non-deterministic path of a certain finite length. Now, don't go crazy and make length 1, because any mathematician or student can do it of length 1, right? It might even be set up so that anything of length 1 is a non-deterministic path. So let's not do that. And probably not 2, but not 500. I'm talking about something like 3 or 4 or 5. And I've actually started to play with some of this stuff a little bit. All right, we can expect to use a computer to actually find such non-deterministic paths. Remember, this is a purely order theoretic situation. I can use a computer to find such non-deterministic paths, assuming the required search space is of reasonable size. When the computer comes up with such paths of modest finite length, I'll call it modest finite length, I'm talking about 8 or 6 or something, it can be viewed as confirming con-SRP in the following sense. If the computer does exhaustive search and it does not find a path, then con-SRP has now been refuted. I've refuted large cardinals. Thus, we have a classic falsifiability setup in accordance with how confirmation works in physical science. Right? Now, a counter argument against this being genuine confirmation would be that it's somehow trivial to find these modest finite length paths. That's the counter argument, that you haven't even joined the thing, right? Like maybe you only looked at paths of length 1 or something, and you said, wow, I found one, therefore large cardinals are confirmed. No, that won't bite. That won't work, right? Maybe finding one packs no punch. However, it is readily seen or felt that even finding or knowing that such paths of modest length exist should be far beyond any human intelligence, if you look at how complicated this stuff is. Invariant maximality has this feel. But how do we justify such an impossibility? These fine non-deterministic paths are readily set up so that the non-deterministic algorithms from invariant maximality are naturally parameterized by data which can obviously be randomized. In other words, I start with some invariant, I start with some order theoretic constraint. That's what invariant maximality is like. I start with some order theoretic constraint, but that order theoretic constraint is a finite object, but there's a large number of them. You can randomize them. You can take a randomized order theoretic constraint. So actually finding the modest length path might be proved to have high computational complexity globally and is only being solved locally during great computational power applied to each instance. By the way, when I use the word high computational complexity here, I meant finite computational complexity. We're not talking about infinite computational complexity, finite computational complexity. This might just lead to an appropriate, well-defined notion of confirmation. So I haven't thought about this completely, but you see what's happening is if I have a randomized modest length setup, I might be able to, if it's modest, use a big supercomputer to actually do the search space and find the thing. But there's no way, but there's no way to actually there's no way to actually get the answer without the computer looking at it locally because the whole thing has got too high a complexity in finite complexity terms. Then I think that we are moving towards some notion of confirmation that we can get our hands on here, and that I'm actually confirming large cardinals. So one of the plans is to actually confirm in a serious sense with some, which itself has some foundation, some serious sense confirm the large cardinals are consistent. By the way, there's always the possibility, because this is falsifiable, that a search shows that it's inconsistent. That's also very exciting, that this can happen. By the way, the human knows that there are these paths of finite modest size, but that doesn't allow the human to actually make any calculations and actually produce any. It's interesting. The computer is needed to run a search and find them. Okay, now I'm only going to do 7 more minutes and remarks on general foundational adventures. Let's go back to my arrival at MIT. Where I saw those textbooks. I was immediately struck by 2 things. One, local. Relatively few exceptions. The individual books did not build up the material with identification of the primitives, clear definitions of each concept from previously defined concepts and primitive concepts, and clear statements of claims. Of course, the exceptions were only some of the math books. I don't think I saw text on computational complexity there in 1964 at that early time. Today, the text on computational complexity would probably also be exceptions. The second was global. Each subject had its own local development independent of the others. Fundamental connections between the different subjects were unclear. How does chemistry relate to physics? How does biology relate to chemistry? All that kind of stuff. How could experts in these various subjects even talk to each other productively? After all, they are on a common mission to discover and organize the truth about the world. So I fixed on the dream of this is me, by the way. This is me back when I was a freshman. Okay, I'm not talking now. So I fixed on the dream of universal foundations. Universal foundations so powerful that it revolutionizes education to the point of universalists being commonplace graduates, if we have the right foundations of everything. Unified foundations. But first, one should set up the foundations for all of the fields individually. So I remember making up the list of subjects for which I would work on their foundations. I always had foundations of math at the top of the list. It already existed, and I was familiar already with, Russell, in high school. I planned my life out way back in 64 to 65. The idea was to further develop the foundations of all fields, one at a time, perhaps spending 3 years on each. I'd already decided to start with foundations of math, and as truth be told, I already spent more than I already spent more than my 3 years on foundations of math. It's more like approaching 60 years. So I'm kind of slow here. But I'm way ahead on schedule for sure. Can I now catch up finally and get serious at age 77? Well, let's see. Looking at this fresh, what is the foundational connection of the various subjects? Well, obviously, foundations of mathematics are clear top of the list. What's next? It seems clear that foundations of computer science is second. This is perhaps mainly due to the very powerfully rigorized computational complexity in all of its facets, quantum computing, all that kind of stuff. However, one should recognize the extreme ignorance that we have about basic relationships between complexity classes. To what extent this could be a foundational challenge rather than a purely mathematical challenge is unclear. There could be a foundational challenge lurking there that people don't even quite recognize that's behind this, like some notion of progressing along you got a computation, some notion of progressing. I don't know. I don't even know. I have no idea. Where is the computer science weakest in terms of foundations? Well, not having thought deeply about this, one thing comes to mind. There should be a universal programming language that is not only particularly friendly to program in, but also powerfully supports proving the correctness of the code. I'm sure there's work all along these lines, but I don't think it's probably not even close to completion, right? This should or could be done in such a way that it greatly enhances the output of programmers. Of course, this is intimately related to the construction of powerful specification languages. Perhaps universal specification languages. Related to this is, of course, the development of powerful decision procedures for more and more powerful little languages. Little engines of proof, I think, is a phrase I've seen by one of the prominent people in software engineering. I was once involved in doing this for string processing. The strategic choice of powerful little languages is the conceptual challenge here. How do you pick these ones that are most applicable to what comes up in programming? It also seems like the watermarking problem in AI is now urgent and may be riddled with foundational issues. In other words, how do you tell whether this was AI or from a carbon-based being, right? This question. So there's a thing called watermarking. They call that watermark. Also, the design and verification of cryptographic protocols is riddled with foundational sounding issues, hiding information, things like that. So what is number 3 on the foundations list? I would say statistics. Not having ever worked in foundations of statistics, I actually like very much what Google AI has come up with. Google AI says issues in the foundation statistics include philosophical disagreements over the nature of probability and inference, the challenge of making accurate interpretations from data, the potential for bias and error in data collection and analysis, and the need to address the fundamental problem of statistical inference where conclusions are based on samples, not entire populations. These foundational issues highlight the need for careful study design, thoughtful interpretation, and awareness of statistics limitations. I kind of like that. Number 4, foundations of physics. Quantum physics makes no sense. So either it makes no sense, either make it make sense, or argue that it can't be made sense, or also address the question of whether it is okay that it makes no sense. I always find the physics courses material surprisingly weak foundationally, and needlessly so, even in classical and relativistic physics, compared to what I expected. Even the fundamental and completely solved classical two-body problem, one sees treatments like the wiki article on it, which makes many intellectual moves, completely standard for anybody good in mathematical physics, of course, without the slightest interest in breaking them down foundationally. I'm not saying that this can't be done in an interesting way, even, just that it appears that physicists don't give a damn. And so the rest of us, without any special affinity for physics, find it too time consuming to get into this stuff. It is inconceivable that any major logician would be so foundationally insensitive. We want to be inclusive. Maybe you can be the first to rewrite basic classical mechanics in a foundationally sensitive way. Physicists won't give a damn, but much of the rest of the world will. We must not forget, by the way, Andrejka and Nemeti, who lead the Hungarian Logic and Relativity School, work on the foundations of relativity. They have a background in math logic in the Tarski School, and they might be the closest to what I have in mind. I looked this up on Google AI, Einstein, on the relationship between science and philosophy, and got extremely thoughtful statements. I had seen quotes of Einstein like this, and I couldn't find them easily. So I rely on, you go to the AI, right? I view that Einstein as a foundationalist, not a philosopher of science, just as I view myself as a foundationalist, not a philosopher of mathematics. So here is some Einstein stuff. Albert Einstein saw philosophy and science not as divergent, but as fundamentally interconnected and mutually dependent. He believed that a deep understanding of philosophical foundations was crucial for scientific progress, and that scientists should engage in critical philosophical reflection, especially when the foundations of their field become uncertain. I think the physicists should actually pay more attention to Einstein. Science without epistemology is, insofar as it is thinkable at all, primitive and muddled. Einstein directly. Epistemology without contact with science becomes an empty scheme, direct from Einstein. I now come to a perhaps used missed opportunity, foundations of engineering. I'm looking around this room and I see chairs, a desk, pieces of paper, books, pens, door with handle, so I can open it, drawers, cabinets, walls, bookshelves, floor, pictures hanged on walls, stapler, a tape dispenser, and so forth. These are all the essential inert static items. They're just usually just not even moving at all, not including lights, computers, phones, and printers. There's a lot of stuff in my room, and yours too. Each of these items really is a solution that evolved over time to a need. How do we organize these needs? How do we have a language for stating these needs? How do we properly state what problems these have solved? How do we prove that these solutions are optimal in the appropriate sense? Like pieces of paper, 8.5 by 11. Maybe the 8.5 11 is an issue, but pieces of paper seem to be a good solution to something, right? Ultimately, we can view all of these items as solutions to combinatorial optimization. How do we cast these in coherent general terms? Hard to see just how to begin this theory. The key is, as usual, to find the right place to begin such a thing. And then there's the foundations of law and foundations of politics. The designing of perfect legal and political systems go back to Plato's Republic. With regard to the law, it seems best to focus on one limited area of law at a time. For instance, patent law. Here, foundational problems such as novelty need to be analyzed. I once hired a patent lawyer and had to pay him, which was the unpleasant part, by the way. And and I saw the state of patent law and I had to deal with some of these issues about what is novel and all that stuff. And this involves an analysis of modes of presentation of devices which spills over into engineering concepts. In politics, an interesting approach is to develop a principled spectrum. Two words here, I don't need this one. Of political systems ranging from extremely limited government to extremely powerful government. I won't even get into the foundations of economics and foundations of biology. And I did promise to talk about piano and chess, perhaps on another occasion. So if you just listen to this talk only because you cared about chess and piano, you're going to be sorely disappointed.
Okay, but we will take you up on this and invite you one more time to speak specifically about piano and chess. So that's okay. Okay, that was wonderful. Thank you very much.
Thank you. You can't do this in a normal venue. This is a very special.
No. It's a special occasion, just designed to be this kind of podium. Okay, so let me just a short remark about your last quick part or last part of your talk. So it reminded me very much, in fact, what Hilbert talked about in his Hilbert problems, because even you talked about foundations of physics. So Hilbert entitled one of his papers on general relativity theory on axiomatic methods in physics.
Oh, yes.
So he considered actually his work on general relativity also a kind of implementation of axiomatic method. And several formulations of his problems were about providing essentially foundations for probability theory and for something else, so for physics and more. So that's so we're still in some sense there. Although perhaps the sense of foundations has evolved over the years since then. But I think it's quite wonderful that logic should be connected to other parts of life, including organizing stuff on your table, so to say, so that it is
logical
optimal.
methods. I would be a little surprised if you could use Ramsey's theorem in your office. So it's not quite it's not quite as it's not just transporting the what we know and love directly into these things. Oh, but the main point is, with this incredible singular success of foundations of mathematics, it's the model. It needs to be the model to guide us into foundations of that are more difficult to come by. I think a foundation of mathematics is great, partly because it's easy. When I say easy, I mean relatively easy. I don't mean easy. It still took thousands of years to get it going right.
Right.
But the point is, without a full understanding of all of the barriers and obstacles that one had in the development of foundations of mathematics, you start with Aristotle with his syllogism. You suddenly, at some point, you realize that this is not sufficient because it doesn't have quantifiers, right? I mean, a deep understanding of how the obstacles were overcome in the history of foundations of mathematics is needed, I think, to set up to do the right kind of foundational work almost anywhere else. So our subject is of the greatest importance. It's at the top.
Okay, before I give the words to other people to ask their questions, so one more thing. So the word foundationalist, did you invent it yourself, or did you pick it up from some other source?
I don't know. I don't remember any place I picked it up. It may be mine. I don't know. By the way, did you run an AI on it? Foundationalist.
Yeah, well, I will. I will check what ChatGPT thinks about
anybody
it.
in the audience could run an AI on that. Google AI or something, or ChatGPT.
Well, I think it's an interesting term. So, but you separate it from philosophy of mathematics, right? So it's kind of.
Oh yeah, yeah. I don't do. Okay, my attitude to philosophy is, it's about philosophy. I like philosophy only when it's pre-foundations. In other words, it's setting up the environment to do something much more serious called foundations. I think that Einstein would agree with that.
Okay. So,
I think Einstein had the right idea. I talk to physicists. I say, look, if they say, oh, all this foundation. No, no, no. We don't want to think about foundation. Don't worry about what quantum mechanics means. Don't. That's not the right way to do physics. Not the right way to think about physics. I said, but what about Einstein? And they always say, oh, well, that was an exception. The answer is, oh, well, Einstein, okay, Einstein was an exception, but this is not the way. This is not the way how physics progresses and so forth. So I mean, I really think they don't listen to Einstein enough.
Okay, please raise hands who wants to ask a question. Okay, Stepan Kuznetsov, please.
Thank you for a very interesting and surprisingly understandable talk. So it's very good if you can understand something not from your background area. I wanted to ask a question about one of these last part about the foundations of computer science. So you're talking about maybe some hypothetical universal language which combines programming with correctness proving. And I see the following like sort of discrepancy here because if you have a universal language, people usually think about something like Turing complete or something like that. But if you want to prove correctness of the programs, then you will, in particular, do something like provably total functions or something like that. And this is a proper class, and this is like a theorem. So could you please comment about on that? What do you really mean about this? What sort of universality you want here?
Oh, no, I don't mean universality in the sense in the computational complexity sense at all. I'm not talking about that. By universal, I mean anybody in any company that has a natural need to get some device built can simply use this language just like anyone else, can use this language very conveniently for their program development. In other words, the language is so flexible, yet it controls the efficiency at the same time. That it goes directly. The idea is you got an algorithm roughly in your mind about how you want to set this product up for market, and you have you sort of know how the algorithm runs and works, but it takes a long time to get that into debugged code that really works. And the idea is to make the conceptual idea of how the algorithm is supposed to work, or how the system is supposed to operate, the conceptual idea of how the system is supposed to operate, to make that as easy as possible to an actual system actually operating. Does that make any sense?
So it's kind of universality in practical sense of the word, not in...
Yeah. This is not theoretical.
So it's like universality for all people need in real life. Like you have like ZFC, which usually, well, some ZFC with some extra axioms, which is not complete, but mathematicians it's sufficient for their needs, like something like that. Am I right?
Yeah.
So
but I want to make it. But I want to make it very close to the way you think. Like I think any programmer, any good programmer is faced with some situation, or program manager maybe is faced with some situation. They're going to have to conceptualize how they want the pieces to fit together and how they're going to roughly work. And they know that the project is not going to be finished in a day. And there's going to be errors in it. And there's going to be a team maybe of 10 people. They're going to talk past each other for a while until they finally get on the same page, and all that. I mean, I've actually done. I was actually at some companies, on occasion, talking to actual people doing this stuff, right? And so people are talking a little bit past each other, and they listen to a talk about how this system is supposed to run, and they don't quite understand. They misunderstand a little bit, so the code has to be rewritten. It doesn't work with with their friends' code and their fellow teammates' code. This kind of thing. You know what I mean? If you have something more profoundly solid and universal, then everybody can sort of conform to it and learn how to conform in it. Uh, that's what I'm thinking. Uh, Now, I happen to know that the companies don't want to stop their programming and create such tools. They want to get their products out. I mean, I actually know this, and but so I think it's up to the academics to actually uh, uh, do stuff like this. Now, I don't know the state of the art. There is. I used to work with. I even wrote some papers with some group that called themselves software engineers at Ohio State, and I actually have some. I'm on some joint papers with them and stuff like that. Software engineering, they had plans like this, but they were much too naive to be anything close to what I had in mind. What I have in mind here, much too limited, much too limited. I don't know if that helps, but I'm not a big expert in this kind of stuff. I haven't really thought about this much. I think Lev has got me to think about it a lot more now than the last few days than I have for a long time.
Okay. By the way, there are some messages in this Zoom chat, but I will leave them for now. But I wanted to ask you the following. So,
Yeah.
example you didn't mention of your one of greatest successes, namely that your theorem on the gap embedding of trees was then used by Robertson and Seymour to prove this graph-minor theorem. So do you expect that some of your more recent things related to this invariance maximality could be used in some
Well,
sort of mathematics?
I more or less said that.
Yeah, but more specifically, can you let's say what branches of mathematics? Okay. What would be the directions of mathematics that this
okay.
would be led?
My feeling is, well, first of all, if there's a way of taking a Turing machine and in an interesting way let it run on a large cardinal, then it opens up a lot of things. But putting that aside, I think that it's likely that one needs to push invariant maximality out of the realm of purely order theoretic and experiment with this, because it's relatively easy to do so, but I don't. It's relatively easy to do that, but I don't want to muddy up the existing stuff until the book is done. Uh, uh, but I think the way I think this might go is this carefully gets put into situations where there's more structure. In other words, right now there's just the rationals with order only. And maybe, the group operations, for example, it has to be put in a context with more, with a little bit more structure, not a lot, just a little bit, and then shown to leading mathematicians who are aware that logic is a serious subject, and that's a certain number of people, right? And I think that they would take this seriously and may well come up with something.
Okay.
This reminds me of blah, 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 or something or other, especially since I have this purely finite development. Like, for example, in invariant maximality, I analyze all of the finite um, all of the finite functions, all of the finite isomorphisms. I mean, I know it's not so clear, but didn't give it details. But and so that was analyzed flat out as a purely extensive piece of finite combinatorics. So similarly, when it's put outside the domain of order, it's going to be some sort of a combinatorial thing with more structure. And this is going to remind somebody important of some situation that they encountered in some way. And then one goes from there. That's how it's going to happen.
Yeah. Okay. Albert Visser,